little f of x and going g of x, and under that process d dx. This notation makes sense? I give you a function and you hit it with a differential operator and you go through product rule, quotient rule, and chain rule. If not so, just think about the very abstract definition of the derivative and you arrive at here, right? So if I give you a number, you do some operation, you get something. It's just like that. Then there's no two answers, right? If I give you f of x, there was only one answer, right? Sometimes this person used a product rule and chain rule to get that, and the other person used a quotient rule only to get the same answer, right? So potentially, they may look different. But as a function, if you sketch the graph of them, they must be exactly congruent, identical copy, right? Although they might look different if you run through different rules. So I hope you understand this g of x is maybe different looking, but it's really one function. Now, going backward process is called antiderivative, right? Antidifferentiation. This is not really the standard term, but it looks like an action term. Unfortunately, there's no one antiderivative. Who can explain that? If I, looking at the g of x, I'm trying to find an antiderivative, there's no unique answer. What I just explained is that if I give you f of x, there's a unique derivative. There's no two derivatives. Derivatives is one, or there's only one derivative. But antiderivative, there's several of them, right? There are lots of them. As soon as you change that c that we just went through, the theorem, there are lots of them, right? So for example, if I give you a x, what was the antiderivative there? 1/2 x squared, remember? But this is not the only antiderivative. There's a plus c. But which antiderivative are you talking about? It's just undetermined, but it's not too bad. It's just up to a constant, right? So this still accepted as a kind of near unique definition. John, did you have a question? Infinitely many, but they're not crazy different. They're all vertical shift, right? So they invented a notation. All right, so we're going to denote it like this. X going backward, right, is this stretched S symbol. Integral, it's called indefinite integral. You remembering this prefix in is very important. Indefinite integral, the symbol is indefinite integral. And you kind of put this dx as a kind of placeholder. The function goes in between stretched S symbol and dx. Dx is not dx multiplied to x. It's just the beginning of the process and end of the process. And what you're going to anti-differentiate is what's inside there. So we know the answer to this one, right? What is it? 1/2 x squared plus c. That's how they write it. This is notation. Make sense? So we're going to develop this backward process. What was the forward process? What kind of method did you learn to this going forward process? Constant rule, constant multiple rule, sum rule, product rule, quotient rule, and chain rule. What do they do in Calc 2? Let's do backward. Backward chain rule, backward product rule, backward quotient rule. The technique of going to the reversing this is like solving a crime. It's a lot difficult than messing up. So that's what we're entering in here. So I'm showing you a few examples. This one we're going through is fairly easy, but next week, probably tomorrow, we hit a little bit of technique, reversing the chain rule. All right, you ready? All right, let's do that. So here's some lemma. Did you hear about this English word lemma before? I think it's a mathematical jargon, only mathematical. This little statement is very useful. It's not like important and serious statement. It's very, very useful. Just like a formula. Like the lemma says that following. If I have f of x and you differentiate it, right? So this is a forward process. And if I do backward, what's going to happen? They cancel, just like inverse function. You do sine and do sine inverse. Then what happened to the input? Nothing happened to the input. Input becomes the output. Now this is a function is our input. We do one process called differentiation. And anti-differentiation, what's going to happen? You get f of x. That's what we get. All right? But because last thing we do is this indefinite integral. We got to add c. That's one little thing. But let's do this backward. What if I antidifferentiate first, then differentiate later? What's going to happen? Yeah, it's an opposite process, undoing process too, right? So what's going to happen? F of x. Last thing you do is d dx, right? D dx is unique. So it's just giving you f of x. The order of this operation, antidifferentiation and differentiation, gives you a little bit of a different result, but it's almost the same, right? It's near unique result. Right, we don't hit a plus c in the second statement. All right, this is an important operational principle which is self-evident. Is that right? Because of the definition of this integral procedure, indefinite integral procedure. So what you do is to go through some of the derivative rules you know and pull out something else. All right, let's start with this one. Number one, d dx of x to the alpha. Who remembers this? Alpha times x to the alpha minus 1. Is that right? Correct? Now we're going to pull out the integral formula. The one thing you have to do is that clear the denominator. Clear up constants, not denominator, sorry about that. Clear up the constants. Then it becomes a neat formula later. All right? You look at the derivative formula in the right-hand side result, kind of clear up the constants. Move it over to the other side. It gives you a nice integral formula. So alpha is a constant, right? Constant multiple. Constant multiple. Sorry about this. Constant multiples. So you divide it. So you go to 1 over alpha times d dx, x to the alpha. Is that right? X to the alpha minus 1. Correct? Good. Then if it is a constant outside the differential operator, can we bring it inside? It's a constant multiple. Constant multiple, you can go inside and out, and differential operator is the same. So here's d dx. 1 over alpha goes inside, x to the alpha. Okay? So now, if you hit integral symbol both sides, nice thing happens. But there's no need to, because we start from here. It's another principle that you pull up a nice formula, is that if the right-hand side has some constants involved within there, just try to simplify it, just like from the beta. Is that all right? Then right-hand side looks a lot simple now, x to the beta. And left-hand side, you write it in terms of beta. Right? So what is that? X to the beta. The beta is alpha minus 1, correct? The left-hand side is d dx. And try to write everything in terms of beta. So what is alpha in terms of beta? Alpha plus 1. You see that? There's alpha plus 1. Correct? What about numerator? I mean the exponent here. It's not alpha plus 1. It's a beta plus 1. Sorry about this. Alpha is beta plus 1. Sorry about that. This is beta plus 1. Correct? We want to write everything in terms of beta. So that right-hand side looks pretty simple. So x to the beta plus 1. Make sense? Now, this is only the derivative rule written a slightly different way, correct? Now, if you hit integral, nice thing happens. So I'm going this way. Integral of d dx, it's operation term, x to the beta plus 1 dx. I hit this indefinite integral operator to the left-hand side. You do the same thing, the right-hand side. Right? Then looks like right-hand side is some formula that we wanted to know. And left-hand side, what happened is with these two things? Differentiate and integral, indefinite integral. They cancel, right? That's exactly what that operation is. You differentiate and anti-differentiate, you cancel. It disappears. So you're left with 1 over beta plus 1, x to the beta plus 1. And left-hand side is x to the beta dx. Correct? And plus Whenever you undo differentiation first and integral later, you have to add plus c in there, right? So we have a formula now. If you want to find the antiderivative of x to the beta dx, no matter what that is, the answer is 1 over beta plus 1, x to the beta plus 1, plus c. We found a formula. Just taking care of a constant multiple, we have a nice formula. Is that right? Yeah. But this only makes sense when beta is what? Is not equal to -1. Makes no sense if beta is -1, right? Yeah. If it is not -1, it makes perfect sense. What if it is -1? You go back and take care of that -1. Okay, the -1 would be, what if it is -1 like this? 1 over x. Does anybody know a function whose derivative is 1 over x? ln x, right? So it's not a calculation, it's just coming from your memory. And our theorem of near uniqueness of antiderivative says the one that you've discovered is the only one, right? That's what it says. Ln x only makes sense in the positive x values. So what if it is negative x value, which makes sense in here? If you go through a piecewise defined function, turns out absolute value inside log takes care of everything, plus c. So homework problem will be that you write down the derivative rules and take care of the constant multiple and rewrite it so that you come up with this integral formula. I will give you a couple other examples to go through this process to come up with this basic integral formula, just like basic table of derivatives. Once you get used to this, and more complicated undoing process will be introduced.